Synthesized iron oxide nanoparticles, IONPs, often referred to as green synthesized IONPs, offer an eco-friendly and cost-effective alternative to conventional chemical and physical synthesis methods. The process generally involves using various plant parts, leaves, stems, fruits, roots, or their extracts. Here are the general steps involved in the plant-mediated synthesis of iron oxide nanoparticles. 1. Plant extract preparation, collection and washing. Select the desired plant material, e.g., leaves, stems, fruits, and thoroughly wash it with tap water, followed by distilled water, to remove any impurities. Drying. Air dry the plant material to remove moisture. Grinding, powdering. Grind the dried plant material into a fine powder to increase the surface area for extraction of phytochemicals. Extraction. Mix the powdered plant material with a solvent, typically distilled water, and heat the mixture, e.g., boiling, maceration, or stirring at a specific temperature, for a certain duration to extract the active phytochemicals. The color of the solution may change, indicating the dissolution of plant components. Filtration. Filter the extract using filter paper, e.g., to obtain a clear, cell-free filtrate. This filtrate contains various biomolecules like polyphenols, flavonoids, terpenoids, alkaloids, and proteins, which act as reducing and capping, stabilizing agents. 2. Nanoparticle synthesis, reduction and capping. Precursor solution preparation. Prepare an aqueous solution of an iron salt, e.g., ferric chloride, ferrous sulfate, at a specific concentration, e.g., 0.1 m. Mixing. Add the prepared plant extract to the iron salt solution. Plant extract to iron salt solution versus V can vary depending on the plant and desired nanoparticle properties, e.g., 1:10, 1:1. Reaction initiation. The mixture is typically stirred and/or heated, often at ambient temperature or slightly elevated temperatures like 60 to 80 degrees Celsius, for a period ranging from minutes to several hours. Color change. A visual indication of nanoparticle formation is often observed as a change in color of the mixture, typically from the original color of the extract to a darker color like black, brownish black, or reddish brown, oxide formed, e.g., magnetite, hematite. Mechanism. The phytochemicals in the plant extract act as both reducing agents, converting ions, Fe to the power of 2+ or Fe to the power of 3+, into elemental iron or lower oxidation states, and as capping, stabilizing agents, preventing the agglomeration of the newly formed nanoparticles. 3. Separation and purification. Precipitation, centrifugation. The synthesized nanoparticles, often appearing as a precipitate, are separated from the solution using methods like centrifugation, e.g., 3,000 to 15,000 revolutions per minute for 15 to 30 minutes. Washing. The collected precipitate is washed multiple times with distilled water, and sometimes ethanol, to remove any unreacted iron salts, excess plant extract, and other impurities. Drying. The washed nanoparticles are then dried in an oven, e.g., at 60 to 90 degrees Celsius, or air-dried to obtain a fine powder. Calcination, optional. In some cases, calcination at higher temperatures, e.g., 500 degrees Celsius, may be performed to improve crystallinity and purity, and to obtain specific iron oxide phases. 4. Characterization. After synthesis, the nanoparticles are characterized using various techniques to confirm their formation, size, shape, crystallinity, composition, and functional groups. UV-vis spectroscopy, to confirm nanoparticle formation by observing characteristic surface plasmon resonance, SPR, peaks. Fourier transform infrared, FTIR, spectroscopy, to identify the functional groups of phytochemicals involved in the reduction and capping of nanoparticles. X-ray diffraction, XRD, to determine the crystal structure, phase, and average crystallite size of the nanoparticles. Scanning electron microscopy, SEM, transmission electron microscopy, TEM, to visualize the morphology, size, and aggregation of the nanoparticles. Energy dispersive X-ray, EDX, spectroscopy, to confirm the elemental composition of the synthesized material. Dynamic light scattering, DLS, to measure the hydrodynamic size and size distribution. Vibrating sample magnetometer, VSM, to analyze the magnetic properties. Factors affecting plant-synthesized IONPs. The properties of the synthesized IONPs can be influenced by several factors. Type of plant extract. Different plants contain varying compositions and concentrations of phytochemicals, which impact the reducing and capping capabilities, thus affecting nanoparticles' size, shape, and stability. Concentration of plant extract. The amount of extract used affects the availability of reducing and capping agents, influencing the rate of reaction and nanoparticle growth. Concentration of ion precursor. The concentration of the ion salt determines the availability of ions for reduction and impacts the final particle size and yield. Reaction temperature. Temperature influences the reaction kinetics, affecting particle size and morphology. Reaction time. The duration of the reaction impacts the completeness of the reduction and the growth of nanoparticles. pH of the solution. pH can significantly influence the reduction process and the stability of the nanoparticles. This green synthesis approach offers numerous advantages, including being environmentally friendly, cost-effective, non-toxic, and biocompatible, making plant-synthesized IONPs promising for various applications in fields like biomedicine, environmental remediation, and agriculture.